I got nothing. Combining continuous functions. Yay! Okay, if f of x and g of x are both continuous at a point, then so is the sum of those two functions. The sequence-based version of continuity is really going to make this proof simple for us. Suppose xn is some sequence that's in the domain of f plus g, which means it's got to be in the domain of f, and it's got to be in the domain of g, and assume it's converging to a. The functions are continuous at a, so since x sub n converges to a and in the domain of f of xn converges to f of a. And since x sub n converges to a in the domain of g of xn converges to g of a. And we already know that if two different sequences have a limit, then the limit of the sum is the sum of the limits. In other words, f of xn plus g of xn must converge to the limit of f of xn plus the limit of g of xn, which we just assumed are f of a plus g of a. So any sequence xn converging to a in the domain of f plus g, we get the limit of f plus g of xn must be f of a plus g of a. Ergo, the function is continuous there. So if f and g are both continuous at a point, so is the sum. Yep, that's really a theme. Our definitions build off one another. Therefore, once you've proven something once, you get to use it later on to make future proofs a lot simpler. So here are some sample problems, okay? By the end of this, you'll have established that rational functions are continuous on their entire domain, which really expands our arsenal of what functions are continuous and where. All right, so if you were able to work through these, remember we already showed in a previous video that f of x equals x and g of x equal constants are continuous everywhere. So by multiplying x's together, we get continuous functions. That's just positive powers of x squared, x cubed, x to the fourth, and so forth. Multiplied by a constant, still continuous. Add those things together, still continuous. And that's how you get that polynomials are continuous. And therefore, once you combine it with that third item on this list, rational functions are continuous everywhere that they actually exist. So now, what functions are continuous? Rational functions. Where? Anywhere they exist. And that's going to give us a lot of mileage. We have one more important theorem to prove about continuous functions. If g of x is continuous at a point and f of x is continuous at g of a, then the composition is continuous at a. So not only can I add or multiply continuous functions, we did that before, we can compose continuous functions and get continuous functions. The proof is fairly straightforward. Let's suppose epsilon is positive. Since f is continuous at g of a, there's a delta so that if y is within delta sub f of g of a, then f of y must be within epsilon of f of g of a. This is just using the epsilon delta version of continuity for the function f at the point g of a. There is a delta, call it delta f because it's related to the function f, so that in the domain of f, if y is within that delta of g of a, then f of y is within epsilon of f of g of a. But delta f is now a positive number and g was continuous at a. So we're going to use the delta f that we generated before and use it as if it was epsilon regarding the definition of continuity of g. So delta f is now a positive number. Therefore, there's another delta so that if x is within distance delta g of a, then g of x is within distance delta f of g of a. So starting with arbitrary epsilon, continuity of f gave us a delta f. Using that delta f as if it were epsilon in the continuity definition of g, we got a second delta, we called it delta g. So overall, what do we have? Just renaming g of x equals y. If x is within delta g of a, then g of x, which is just y, is within delta f of g of a. But now I have y within delta f of g of a, and therefore f of y within epsilon of f of g of a. Overall, if x is within delta g of a, then f of g of x is within epsilon of f of g of a. The function is continuous. The composition function is continuous at a. Yep, x is close to a. Because g is continuous, g of x must be close to g of a. Because f is continuous, f of g of x must be close to f of g of a. That's the gist of it, indeed. Another proof. If g is continuous at a and f is continuous at g of a, then f of g of x is continuous at a. Same theorem, we're just going to prove it a different way. So suppose A is any open set containing f of g of a. F is continuous at g of a. A is an open set containing f of g of a, which means f inverse of A is open. We're using the topological definition here. A is an open set containing f of g of a. Therefore, f inverse of A is open. And f inverse of A certainly contains g of a. So now we have g of a belonging to this open set preimage of A under f inverse of A. But G is continuous, so if I have some open set containing G of A, its preimage under G is also open. G inverse image of F inverse image of A must be open. Overall, F of G of A is in the range of F. Since F is continuous at G of A, if I take an open set containing F of G of A, its preimage under F is open. But now I have an open set containing G of A, and since G is continuous, the preimage of this open set is also open. So overall, what did we do? We took any open set A containing F of G of A, and we took its preimage under the composition. F of G inverse is G inverse of F inverse. This is the result about composition of functions that you may or may not have worked through before. So since we have shown that G inverse of F inverse of A is open, that's just F of G inverse of A. So for any open set A containing F of G of A, F of G inverse of A is open, and that's exactly the topological definition that the function is continuous. And there it is. The topological definition of continuity actually made this proof a little simpler, in my opinion, than the last one. Which is a good reason to remember that it's around. A lot of times, things that you're asked to prove, if they sound very abstract and general, then the very abstract and general definitions might be handy. So this statement, G is continuous at A and F is continuous at G of A, and therefore F of G of X is continuous at A. Could we have used the sequence version? Yes, it's actually not that hard. Could we have used the epsilon delta version? Yes. Okay, we did it on the previous slide. But it's a very general result, and the topological definition also makes this proof fairly straightforward. Work through the following sample problems. Also, leave comments, subscribe, notification thing, all that. So now we've got some sample problems, a lot of counter examples to try to violate some bad assumptions students make. Okay, so a lot of these theorems, for example, if f and g are both continuous, so is f plus g, don't necessarily work in the converse. So these counterexamples should have helped you avoid these converse errors. And the last one, show the absolute value function is continuous. A nice little exercise, and we'll use it later on anyway. We can take the previous notion of one-sided limits and apply it to continuity. Okay, so if the limit as x approaches a from above of f of x is f of a, or the limit as x approaches a from below of f of x is equal to f of a, we call those respectively right continuous and left continuous at x equals a. So for example, if I have a function that looks something like this, and then it stops. Okay, I can't take x approaching a from above, I'm not even in the domain, but I can take x approaching a from below. So if x approaches a from below, and I'm evaluating f of x, then I am approaching this value right here, which is f of a. So this function is continuous from below or left continuous at a. But I can't call it right continuous because I can't even approach from above. I'm not even in the domain, which also means I can't call it continuous. Okay, so for example, the square root function, the domain just sort of ends, but it is right continuous. Okay, we do tend to say that if you're continuous on an interval and right or left continuous at the endpoints, whichever one is relevant, okay, then we just sort of say you're continuous on the interval. At an endpoint of an interval, that might be a cutoff point of the domain. Since you can't approach from both directions, we implicitly know you're not going to be able to even define continuity there. But if you have the appropriate one-sided continuity at the endpoints of the interval, just as convenient shorthand, we say, oh, you're continuous on the interval. You're genuinely continuous on the interior, and at the endpoints you have whichever one-sided version makes sense. So the square root function we can call continuous on the interval from 0 to infinity, including 0, even though at x equals 0 we only have right continuity because the domain doesn't extend to the left. But just as convenient shorthand, we say continuous from 0 to infinity, because at 0 we know we could only possibly mean right continuous. Yeah, I mean, we've had one-sided limits, so sure, we've defined some stuff. It's just a convenience when we're dealing with intervals and their endpoints for most purposes. Okay, a much shorter video this time, hopefully a bit more pleasant. But what we've seen is, having worked through abstract definitions of continuity, we get a lot of convenient results fairly quickly. So come on back, we're going to keep talking about continuous functions.